Hi guys, and welcome to today's YouTube video course. In today's video, we're gonna see the static variable user in C programming. Our main focus will be the static variable user and declaration within an embedded C-based project. Therefore, we'll need first of all to set up an embedded systems based project to show how we can use those static variables within such project and what is the main purpose of such static variables. So we'll start by showing how to set up the different tools and project to be executed by an STM32 microcontroller. So the STM32 microcontroller will be our hardware to execute the embedded system based project that will be used to demonstrate all the theory and the concept related to the static variables. Then we'll start by explaining the exact definition of static variables in C, as well as showing the different types of static variables like global static and local static. Then of course we'll finalize this YouTube course by running a set of examples to demonstrate what we have learned across the different slides here and to show up how those global and local static variables are acting and working. For the STM32 project setup, we'll need first of all a hardware to run the different examples within the scope of this course. I will use an STM32 L4 Nucleo board to run the different examples. However, and because the different STM32 microcontrollers are quite similar in terms of memory layout, then you can use any other STM32 microcontroller to run those examples. Now the different tools needed to build our STM32 project will be located within this Wadix technology GitHub repository, and this is the link to the GitHub repository. Finally, the makefile project needed to compile our embedded C sources to generate the final image to be loaded into our STM32 microcontroller will be located as part of the Wadix technology GitHub repository, and this is the link to the GitHub repository. The link to the different slides as well as the course materials and project will be provided as part of our YouTube video description. We'll need now to clone and check out our Wadix tools GitHub repository under C drive. My recommendation is to pick up C drive because it offers short paths to the different tools and applications to be used out of our tools directory. Now in terms of tooling, our Wadix tools GitHub repository offer quite big number on terms of toolings and applications. Nevertheless, for our makefile based project, we will need mainly the arm-GCC compiler. This is the arm-none-eabi-gcc compiler from ARM, and this is targeting mainly the ARM Cortex-M microprocessors family. Our makefile project will be an ARM Cortex-M3 based project. Then we'll need this GNU Win32. This one does contain already our GNU make build tool. And finally, we'll need set of tools and applications to be used in combination with our make file. So those applications will be used as part of our makefile rules to create directories, remove directories, copy files, change or modify existing files, and so on. Cygwin64 does provide those set of applications. Example, we can create directory via this mkdir application. We can remove via rm as well as rmdir for directories, and so on. Now we'll need to set up our Windows environment variable path to point to those applications and tools. Hence, the Windows system will be able to recognize the location of those tools and applications once they get invoked via the command line. For that, I have prepared this PowerShell script install environment. Once executed from a PowerShell session, then the Windows environment variables for the current account will be updated to point to our applications and tools needed by our project. If you want to revert back, then you can use this an installation environment PowerShell script. So this to install, and this is to restore back the old paths. To execute those scripts, you need first of all to open a PowerShell session. So like this, as you can see. Then the first thing to be done within the current active PowerShell session is to enable the execution policy. This one enables PowerShell to accept external scripts and execute them. Without running this command, the PowerShell session will block the execution of our PowerShell installation script. Once we executed this set execution policy, we can navigate to our tools directory. Then we initiate the execution of our installation PowerShell script. Once done, the Windows environment variable path will be updated and pointing to our applications. So if we inspect the environment variable of our account, then we go to path. As you can see, the path has been updated to point to our Cygwin64 applications as well as make build tool as well as the arm-GCC compiler. If you want to revert back, then you can just execute the uninstall PowerShell script. Now if we inspect again, as you can see, the previously added tools has been removed. Now I will just execute again this install PowerShell to be able to move forward within our makefile based project. As you can see, this has been added again. Now we can move forward and check out our makefile based project. A static variable in C or C++ is a standard C or C++ variable whose lifetime will be the full or entire program run. Hence, the static variables will be destroyed only if the current running program finish and end. The different static variables will be automatically initialized to 0 or null for the case of pointers if we don't explicitly initialize those static variables. Because the lifetime of those static variables will be the entire program run, then the content and the state of those static variables will be kept across the different function calls. Finally, what is more specific about those static variables compared to the standard C variables will be the limited visibility. Means, if we declare and define a static variable within a C source file, then we try to import those static variables on another C file, then this kind of import will fail, simply because the visibility of those static variables will be limited to the C file that declare and define those static variables. We have two types of static variables within a C program. First of all, we'll have what is called static global variable, and then we'll have what is called static local variable. Both static variables, whether global or local, will be limited in terms of visibility to the C file or source that declare and define those static variables. A static global variable is just a normal C global variable that is defined globally outside the scope of different C functions, but will have this static type qualifier. So this static global variable is quite similar to standard C global variable, but it will have in addition this static type qualifier. On the other hand, a static local variable is quite similar to a normal C local variable that is declared within the scope of a function. However, it will be marked with this static type qualifier. So as you can see here, this one is just a C local variable that is used within the scope of this C function, but on addition will have this static type qualifier. Now, in terms of functionalities and what are the major differences between static global and local global, a static global variable in C is a global C variable that has been declared outside the scope of any function. And this globally declared C variable will be marked with this static keyword. Once declared globally, this static C global variable can be used anywhere within the scope of the .c file source that declare this global static variable. However, it cannot be exported outside the scope of the .c file that declare this static global variable, simply because the visibility of this static global variable will be limited to the C file that declare it. The lifetime of static global variable will be the whole program run from the start to the end. The main purpose of using those static global variables is to hide those global data variables from other C translation unit. So here we are encapsulating those global variable that are marked with this static keyword within the scope of the C file that declare them. Hence, they're gonna be hidden from outside C translation unit. And by translation unit, we mean the different C file that get compiled and try to import those static global variable. And such import, of course, will fail because those static global variable are hidden and again limited in terms of scope to the C file that declare them. On the other hand, a static local variable in C is just a C local variable that is declared inside a function or a block, and it will be marked with a static keyword. The static local variable can be used only within the scope of the function or the block that declare them. So this is quite similar to standard C local variables. However, what is more specific about those static local variables in respect to the standard C local variables is that the lifetime of those static local variables will be the entire program from the start to the end. So they will not be deallocated or destroyed on each call. And this is quite different from the standard C local variables, where the allocation and the lifetime of those local variables will be only the current function call. And because the lifetime of those static local variables will be the entire program, then it keeps each state between the different function calls. Means we will remember from one function call to another the previous state of those static local variables. Hence, if any update occur to those static local variables in a function call, then the next function call will remember the latest update that has been done to those static local variables. So this is our check it out embedded C project, which is targeting an STM32 microcontroller. As you can see, this is a makefile based project. And the makefile here consists of set of rules needed to compile the different C files, generate the different object files out of them, and finally link the different object files to generate the final ELF image to be loaded into our STM32 microcontroller. The toolchain to be used will be the arm-GCC based toolchain. Those are our compiler flags, as you can see, and those are our linker flags. Now, those are the different C files needed to create this image targeting the STM32 microcontroller. We'll have the startup code, which consists, of course, of this vector table. And the vector table is the first thing to be fetched by our ARM Cortex-M microprocessor to boot properly our device. And the first two things to be fetched out of this vector table will be the top of the stack and the reset handler address. The top of the stack, which is the first element of our vector table, will be used to initialize the processor stack pointer. And the reset ISR, this address will be used to initialize our program counter so that the first thing to be executed will be our reset ISR handler. And here, after we do the BSS and data initialization, we'll jump right away to our main function. And this is, as you can see, our main function. And this one is just an interface to jump to the different examples prepared within the scope of this video course. Here we'll have basically 3 examples. One to show up how we can declare a global static variable and how the content of this static variable will be updated and remembered on each function call that will update this static global variable. We have as well another example to show up how we can declare a static local variable within the scope of this C function, and how this static local variable will be updated only on each function call that has declared this static local variable. So this local one is not visible for the different functions defined within the same C file, as well as the different outer C files that try to import this local static variable. So this one is visible only to this function and will be updated on each call of this C function. And finally, we'll have an example to show up that this static global variable will be marked as local attribute, and the normal C global variable will not be hidden and will be marked with the global attribute. Local or global, this is basically a marker that we can see it whenever we try to disassemble and generate the different symbols within our ELF image. So this one will not be executed by our STM32 microcontroller, but will be used to generate a final ELF image. Then we'll try to dump this ELF image, generate the different symbols out of it. Then we'll inspect this marker attribute that has been assigned to the static global variable as well as the standard C global variable. This README file within the project will contain instructions on how to compile each of the examples supported by our project. We'll start first of all by compiling and building the first example that demonstrates how we can declare a static global variable in C and how this static global variable will be used and how it is working on a real hardware. Now, after compiling and building our project example, we'll have this build subdirectory created. Here, we'll have the final example.elf file, which will be loaded within our STM32 microcontroller. Beside this .elf, we'll have set of files that helps us to inspect the different symbols and assembly code within this elf file, like the disassembly file and the symbol file. And of course, we'll have the map file. Finally, we'll have a Keil project that will be generated at build time, and this one will be used to load the binary into the STM32 microcontroller and will be used as well to debug it. We'll start first of all by loading the image into our STM32 microcontroller. Then we'll hit the debug button to start a live debug session. So single step, then we'll jump into our example. Now here I have declared this static global variable. Now if I try to inspect this variable in a C window, we'll see that by default it will be initialized to 0, simply because I haven't explicitly initialized this variable with different value. So the default will be 0. Here I have a function that will increment this static global variable by a value that is provided as input parameter to this function. And in my example, I am invoking this function 3 times, trying to updating this static global variable. The whole idea is to see that from one function call to another, we'll be able to observe that the content of this static global variable has been preserved based on the latest update. Now let's jump to the first call. This will update the static global variable by 3. And here we go. So the new content and value of our static global variable will be 3. Then we'll update the static global variable by 10. This 10 will be added on the top of the previous update, not the initial value. So the expected out result will be this time 13. And here we go. 13 in hexadecimal will be 0xd. And finally, we'll do a final update by adding 2. So 2 plus 13 will be 15. So in hexadecimal will be f. So as you can see, this static global variable is visible within the scope of this declared C file. So the C file that declare the static global variable can use this static global one without issue within the same scope. And any function declared and defined within the scope of this C file can use and invoke those static global variables. And the static global variable content will be preserved the whole lifetime of our program. And from one function call to another, the latest update done to our static global variable will be preserved. In our second C example, we'll see how static local variables are working at hardware level. A static local variable is a local variable that is declared locally within the scope of a C function and will be marked with this static keyword. Compared to static global variable, a static local variable will be limited in terms of visibility to the C file that declares them, as well as the C function that has declared those static local variables. So here the limitation in terms of visibility will not be only at the C source file level. Actually, it will be even at the function level that has declared those static local variables. Now, compare it to a normal C local variable. A static local variable will preserve the last update of the content and the state. So the context of those static local variable will be preserved from one function call to another, which is of course different from the standard C local variables, where the context of the declaration and assignment of the normal C local variables will be destroyed from one function call to another. This means simply, in our case, that the new value to be used to increment our static local variables will be added on the top of the latest update, not the initial value. Now I have declared this global C variable to keep track on the different updates to be done on our static local variables. The reason behind this is that while debugging, it is a little bit tricky actually to watch the update on the different local variables within a C function scope. Hence, we'll need a global variable to track this update. Now we'll start by building and compiling our project. This is our Keil project. I will load the binary into the flash memory of our STM32 microcontroller. Then we start a debug session. Single step. Now I will try to dump into the debug watch window the content of our debug global variable, and this one will be used to track the update done on our static local variable. Now I will execute my function the first time, and as you can see, this debug global variable will contain this value 3, and this is matching the value used to increment our static local variable. So this is actually reflecting the value now contained within our static local variable. Now if I execute my function the second time, we'll see that the static local variable has been updated by this value. So in total we'll have 13. The hexadecimal value of 13 will be 0xd. And as you can see, we have preserved the last update done to our local static variable. Hence, the 10 has been added on the top of the 3, not on the top of the initial value. If we continue, then we can see that this 2 has been added on top of the value 13. So the end result will be 15. If this local variable was not declared as a static, then most likely it will be overwritten at certain point by another call, because with the normal C local variables, the previous update or state is not mandatory to be preserved, not like a static local variable. Finally, in our latest example, we'll see the differences between a static global variable and a normal global variable when it comes to the different symbols attributes assigned to each one of those. Now in this example, I have declared two global variables. One is a normal C global variable, and the second is a static global variable. Now I will try to compile and build this example. So this is done. Now we're gonna try to inspect the outcome of this build process, and to be more precise, we're gonna inspect the symbol file generated out of the ELF image. So this file will be generated thanks to this command. Read ELF to generate the different symbols and attributes assigned to each of those symbols out of our ELF image. And those are the read ELF flags used to generate this kind of symbols. Now, if we inspect this file, we'll see a summary of the different symbols within our ELF image. And here, of course, we'll be more focusing on those two global variables. Now, if we try to look for the normal C global variable, we can see that is marked with this attribute global. And now if we try to inspect this static global, then we can see obviously that is marked as local. So the major difference is that the visibility of this static global will be limited to the C file that declare it, and hence we cannot export it to the other C files, and the exportation will be only possible with the normal C global variables.